So here are a few notes on section 3.1. And this is a sketch, and we've seen the sketch before when we were in section 2.4 talking about the slope of a line at the point, or the tangent line, the slope of the tangent line, or the slope of the function at a point. And again, this is my function, f of x. And if I have a point A and a point B, and I can call B a plus h, if the change in x here between a and b, or delta x as we call this h, then this distance is h. If this is a plus h, this point, b. And we can label these points on the graph apparently. So this is a, and this is f of a. The function gives us the vertical position. And this is the point a plus h. All right, and it has the height of f of a, and up here this is the point a plus h and the height f of a plus h. And you can see your vertical value of your function, or the value of your function, f of x, a plus h, and this is just f of a. So again, this point is a f of a, this point is a plus h, f of a plus h, and just for your information, this is the point a plus h, horizontal value, and f of a, vertical value. And if we take the slope, that's the change in y over the change of x, that's just going to be the change in y, so that's going to be f of a plus h minus f of a. That gives you your change in y. And your change in x will be a plus h minus a. And if we simplify that, we get h. So this is basically our slope of the secant line. And if we take the limit as we get closer and closer, we talked about this before, as we get closer and closer, I guess I can use a ruler to show you this, as delta x or h approaches 0, so as this distance gets smaller and smaller and smaller, the slope of that secant line is going to eventually get closer and closer to the slope of the tangent line. So we say the limit as delta x approaches 0 of the change in y over the change in x, or the slope, which is the same thing as the limit as h approaches 0 of f of a plus h minus f of a over h. These are the same thing. That's actually going to be the slope of the tangent line, or m. Okay? And that slope at the tangent line is called the derivative. So we formalize that as the derivative. And you can read this on page, in the book, I think it's on page 98, 99. And then here you go. And this is our definition of our derivative. The derivative of the function f with respect to the variable h is the function f prime whose value at x is given by the limit. Now what we're going to do is we go back to this picture, and instead of using a particular value a, we're going to let x be any value x in the domain. So rather than being restricted by 1a, I could pick any number here and do the same thing. So instead of using a, I just put x. So just put your x there, and that's going to give you the definition of the derivative. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. And again, this is the slope. This is the change in y over the change in x. And that's always provided the limit exists. And we'll be talking about that a little bit later. And then we've got some details over here. If f prime exists, we say that f has a derivative, or f is differentiable at x, and a function that is differentiable at every point of its domain is a differentiable function. And this is in your book, so you can take a look at it. And let's take a look at an example. And it's very similar to what we did with the slope of a function at a point, using the definition. So I've got one worked up here. There is an example in the book that's a little bit different. Please see the example in the book because it uses a cubic, and that's good to know. So here's our example over here. Let's say if f of x equals 3x squared minus 5x plus 2, find f prime of x. So very similar to what we did in section 2.4 is we write down the formula. In this case, it's f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x. Now I don't have to put the a in because it's not at a particular point, so this is one less step than we've done previously. So I just put the x plus h into the function. So 3 times x plus h squared minus 5 times x plus h plus 2, because that's my function, 3 times something squared minus 5 times something, so my something is x plus h, so 3 times something squared minus 5 times something plus 2. And then minus f of x, and this is your f of x, so it's right there. over h. And then we can multiply this binomial out. And I wouldn't skip this step just to be safe. So 3 times, and this is going to be binomial squared, so first term squared, plus twice the product, plus the second term squared, and we can multiply these out. Negative 5x, negative 5h, plus 2, and then I can remove the parentheses, so I have to change all the signs. So this is going to be negative 3x. A negative times a negative is positive 5x, and negative times a positive is negative 2 all over h. And then I'll multiply this out, and I can simplify 2 minus 2 is 0, so that goes away. So I can do a little simplification there. And now I have the limit as h approaches 0 of 3x squared plus 6xh plus 3h minus 5x minus 5h minus 3x squared plus 5x, and remember the 2's zeroed out. And then we can, again, zero any terms out, so we have 3x squared minus 3x squared, that becomes 0, and negative 5x plus 5x, that becomes 0. So what's left is the 6xh, 3h squared, and minus 5h, all over h. Now, anytime we want, we can take these limits. So if we take the limit over here, we're going to get 0 over 0 still. And anytime you want to try to evaluate these limits, you're going to get 0 over 0. Because we have a factor of h at the top, and everything else is going to zero out. So we're always going to have a factor of h until we factor that h out here. Remember, when we have 0 over 0, we can factor and resub, so I'm going to factor the h out. And that's going to leave me with 6x plus 3h minus 5. And now h over h is 1. I'm still going to have 0 over 0 until I do that. And once I have that, we're in good shape. This just becomes 6x plus 3h minus 5. I can substitute 6x, 3 times 0 minus 5, and 3 times 0 is 0, so that just becomes 6x minus 5. And there's your derivative, or the slope, at any point. So you can pick 3, 4, 5. You can find the slope of your function at any point, x, something. So with any x value, all right? And if you want to find the y value, you have to put that back in the function. So you can find it at any point given the x value. So all you need is the x value to find the slope at a point where x is something. If you want to find the y value, you can put that back in the function. So there you go. That's a good example. And we'll probably have a quiz on something like that. So I hope that makes sense.